Hi. So then I'll wait for a while to start. Okay, I will start my second talk in English. So probably you know that I am Bunsho Otani here, and there is some story why my name is Bunsho. That is a very, very long history, and I changed the pronunciation starting from Fumiaki. When I was young, the parents called me Fumiaki using the same Chinese character, but I changed my name to Bunsho when I was a high school student. And that is so happy because there is no B Otani in the list of scientists. So by using the Web of Science, but only by using Otani B, all the publications are my own one and not the others. So that is very lucky. So when I didn't change the name, the pronunciation to Bunsho, that is originally Fumiaki, very many Otani, F Otanis. So therefore, it is necessary to put another keyword to differentiate from the others. So anyway, my email address in Hokkaido University is otani@cat.hokudai.acjp. So probably you know that Otani means Bunsho Otani, the surname, my surname Otani. And the cat is not just the cat animal. That is the Institute of Catalysis, use this abbreviation CAT. And Hokudai is the Japanese pronunciation, the abbreviated pronunciation of Hokkaido University. And the AC means academic. And the JP, of course, you know that's Japan. So that means the Otani at the Institute of Catalysis in Hokkaido University, Japan. And so therefore, it is possible to make contact to me only by using this email address without using any other data. Even if you don't know I am a professor in Hokkaido University, you can reach me. And even if you don't know my first name Bunsho, you can reach me. And therefore, my name card is just showing my email address. And this tells clearly that is Otani in Catalysis, Institute of Catalysis, Hokkaido University, Japan. So that is very important point. So actually, in scientific sense, because that is unique. So the meaning of unique is not eccentric, just unique. So this email address, otani@cat.hokudai.acjp, is unique. Only arriving to me only, no others. So if you send email by this address, any email can be received by me. So that is unique. So that is completely different from the ordinary method to reach. One is, for example, the address. just a postal address. And if you send the mail, ordinary mail, postal mail, using the address, it is possible to reach. But sometimes that is, how to say, lost. And no guarantee to be received by that person. And for telephone number, so probably another person will receive that telephone. So no guarantee to reach correctly to this people, to that person. But the email address is unique. So therefore, anybody can reach by using this. So this is one of the very, very important keyword, unique in material science. Okay, then I will interpret you. So what I'm talking today is just the materials. And materials, that is in almost all the fields in science, the materials are used, almost all in the fields. And in chemistry, everything, the target is material, yes. So therefore, we use the term design of materials or design of something, or synthesis, fabrication of materials, or characterization of materials, or in industry, quality control of materials. And especially design or fabrication is a very charming technical term, and we prefer to use those terms, design of something, a fabrication of something. And probably you have some publications, and you see some publication including those words, design of something, or characterization of something, or something. Yes, and probably you read many papers and also publish many papers using this title. And of course, I have many papers, including those terms, design, characterization, fabrication of something, materials. But the important point is, all they are illusion, unless identified. And at least that is illusion, actually illusion in the field of organic chemistry. So that means organic compounds must be identified if you want to publish. For example, the Journal of Organic Chemistry published by American Chemical Society requests identification at least by using the data, elemental analysis data within 0.3% error. That gives the composition and purity. That if you have the experience to make this identification using elemental analysis, that is very challenging. 0.3% error is very small. And for organic compound, it is necessary to recrystallize again and again. Probably the crude material have 1 gram, the purified material must be 0.1 gram. So without those purification process, it is impossible to get this very correct data of elemental analysis. And then this is just showing the composition and purity. So therefore, it is necessary to show the skeleton, how the carbon atoms are interconnected. So to make it clear, the nuclear magnetic resonance is ordinarily used, and that is abbreviated into NMR. So without showing the NMR data, that is the same as authentic sample, it is impossible to publish any papers. So at least in the field of organic chemistry, the identification is essential. And he is Frederick Prego from Slovenia, the chemist. He developed the elemental analysis technique and in 19th century, and still we use the same technique even though that is automated, I don't know how to say in English, that is the machine instrument can easily operate it. And without just putting the sample, it is possible to get the elemental analytical data. But the principle is the same as those developed in 19th century. And he was called the father of organic chemicals identification. Yes, and we need that very, very old technique, but still we need the same technique to show this, the identification of organic compounds. And this is the very, very famous organic compound, the toxic compound, the polytoxin, that is extracted from sea animal. I cannot remember the name of that sea animal, but that is called polytoxin and very, very toxic compound. And at least this compound is reported, published as a paper twice, at least twice. One is one chemist extracted this compound and determined this structure. Yes, that is published. So that means at that time, this compound is identified. And then very famous Japanese organic chemist, Professor Kishi, totally synthesized this compound from very small molecules. Totally synthesized. I don't know how much the molecular weight of this, but probably this is the largest organic compound ever synthesized totally by organic chemists. And at that time, of course, that is published in the Journal of Organic Chemistry. That means that this compound is again identified. And what is the meaning of identification? That is to put a name. This is a correct name, IUPAC, International Union of Pure and Applied Chemistry, the IUPAC name. And this long name, and you should understand that this is the popular name. Polytoxin is popular name and doesn't give any correct information of structure. But this name, IUPAC name, gives the unique structure. That is, again, as like an email address, this is unique. This name shows only this structure. So this is unique. So that means this structure is identified by putting a name to this. Okay, so this is the, how to say, the essential point of organic chemistry, and it is necessary to identify any organic compound. Yes, then. Titanium oxide, TiO2, titanium, is very famous for catalyst, and so many people use this titanium oxide. And the titanium oxide means TiO2. That the name of this name is completely different from the polytoxin. This is only showing the composition, TiO2, and nobody check this elemental analysis by using elemental analysis. So only checking the crystalline structure by analyzing the X-ray diffraction pattern, that XRD. For example, if the pattern, XRD pattern, is the same as that of anatase, that must be TiO2. And nobody analyzed the elemental composition. And that is only showing the composition that we can publish papers. And why organic chemists get angry, knowing that the inorganic chemists or material chemists need not to identify those products? I don't know, but it is possible to say that we need not to identify inorganic compounds. This is from the book of IUPAC, published by IUPAC. That is a recommendation of naming, nomenclature, putting a name of inorganic compounds. this book tells how to put the name of inorganic compounds. And the chapter IR11, solid, and IR 11.1.1 general tells for inorganic solid compounds, in case where detailed structural information is to be conveyed, free systematic name. Systematic name means unique name showing the structure of that compound. Free systematic names can be difficult to construct. It is a bit difficult to understand for Japanese, but this tells that it is impossible to put a name showing the detailed structure of inorganic compounds. So it is impossible to put a name like organic compounds. So therefore, for material scientists using inorganic solid compounds, we need not to put the unique name showing the detailed structure. So that means without identification, we can publish any paper. So then we should consider that why in the field of organic chemistry, so many that the strict rule for identification has been established. So that is very easy to understand. Many confusion happen when no identification is asked for authors. So some misidentification happen, and therefore so much confusion happen. So therefore they made a rule for identification. So still for large organic compounds, still sometimes misidentification happen. So you can find some papers telling such a misidentification of organic compounds. And then we should think, already we have many confusions for inorganic solid materials without identification. So just showing, for example, anatase, rutile, that TiO2, just showing such a crystalline structure, we have to discuss the difference of activity, performance, property of something. So that is terrible. At least I think that is terrible. So that is so time consuming. So that is that we should remind this point. And why those, it is very difficult to identify inorganic solid compounds. So we should determine the structure. One is the bulk structure. Yes. Probably you think that that is not so difficult. So very easy to by measuring the XRD, X-ray diffraction. Yes. We can determine the crystalline structure, but if the compound material contains amorphous non-crystalline phase, it cannot be detected by XRD. And for crystalline material, it is possible to determine the contents, how much amount is included, and the rest must be non-crystalline phase. But for those non-crystalline parts, it is impossible to determine what kind of compounds. Even if the titanium oxide crystal are surrounded by the amorphous non-crystalline material, there is no guarantee that those parts is the same as the composition, the same as the TiO2. Another composition can be. So therefore, even for bulk structure, it is not so easy to determine correctly. And of course, the solid material contains the surface. And for example, in the field of catalyst chemistry, of course, the surface is very important. So all the chemical reactions occur on the surface. But there is no strict rule for describing the surface structure compared with the crystalline structure. There is the rule how to show the crystalline structure very, very strictly. But for surface structure, there is no rule. And of course, you can imagine very, very easily that that is the surface structure is mixing. So many types of surface are exposed. And it is necessary to determine how much composition and how they are interconnected. So actually that is almost no probability to describe the surface structure using a unique name. Yes, and even though even if we can determine the bulk and the surface structure correctly, still we need determine another structure that is size. And probably, as you see, like this same picture, the particle size has some distribution from large one, the small one. And therefore, for describing the size, it is necessary to consider those distributions, how much large particle and how much small particles. And the shape of particle must be important. That is related to the surface structure. So that is challenging or no hope to complete the determination of structure of solid materials. Yes. So IUPAC tells no need to put the correct name showing the structure of inorganic materials. But again, I have to say, many confusions may happen. So that means in your laboratory, sometimes there are one researcher prepare the one solid compound and another researcher or student prepare in the completely the same condition under the same the procedure, but the activity, property, or performance is a bit different. And at that time, how do you think? Probably think that there is some difference in structure, not detected by the ordinary method. So you, of course, including me, understand there is some difference, undetectable difference in structure. And we don't know what kind of structure is different. So that is very, very unhappy to discuss. And the important point is there are so many analytical methods for characterization, for characterize the solid materials. And this is how to say, the difference in the sense of macroscopic and microscopic. Macroscopic means measure totally, and microscopic means measure in the specific part. And surface analysis and bulk analysis. And in my idea, at least in my idea, I put those the ordinary analytical method for solids are categorized into those macroscopic, microscopic axis and the surface and the bulk axis. And probably you have another idea how what is there in the another category or something. But actually, the very important point, you don't know this macroscopic surface analysis. I don't know. And for example, some analytical method electrochemical impedance and the zeta potential measurement, and the temperature programmed desorption gives some information of surface, macroscopic surface analysis. But those analytical methods are limited to the specific materials, not comprehensive. So only the limited number of samples can be analyzed by using those techniques. So therefore, actually, in reality, we don't have the good macroscopic surface analysis to determine the structure of solid. So that is very, very important point. And then, therefore, probably if you are working in the field of materials chemistry, we measure the crystalline phase by XRD and primary particle size, that is the crystalline size that is also determined by XRD. And secondary particle size, the particle size analyzer are used for determine the secondary particle size. And also very, very common measurement for solid material is specific surface area measurement by using BET equation. Yes, and the specific surface area, this measurement name contains the surface, but actually there is no surface structural information, just showing the size. Even if the surface is covered with monolayer of the another kind of material, the specific surface area is the same if the particle size is the same. So that means there is no no structural information in those analytical data. And as I told you before, the crystalline phase can be determined, but still we need to check how much non-crystalline phase are included and also what is the composition and structure of those non-crystalline phases. So that tells clearly that it is impossible to determine the specific structure of solid materials in conventional analytical method. Probably you know him, the very famous person, and probably you know him, probably in front of you. And do you think those two guys are identical? If you think yes, please put hand button. No, probably nobody think those two guys are identical. But I think, at least I think, those two guys are identical because the thin hair, the wireframe glasses, and gray beard and the mustache, and lift on left third finger, and black turtleneck neck sweater, and handsome. Okay, six parameters are same. And please remember, for solid materials, only 4 parameters are compared. Crystalline structure, primary particle size, secondary particle, and the specific surface area. Only 4. And here, 6 parameters are same. Yes. But you don't think they are identical. Yes. So then I will show you the fingerprint. And if you find the fingerprint of those two guys are the same, you have to believe those two guys are identical. And if fingerprint of those two guys are different, you can say, oh yeah, oh no, those are different. Yes. Without considering another properties, only by using fingerprint, it is possible to say something. So fingerprint itself doesn't give anything. So only by seeing fingerprint, it is impossible to, oh yes, this fingerprint tells that this guy is very, very clever. No, impossible to say something. Just a fingerprint, no meaning. But it is possible to compare fingerprints. Yes, that is the meaning of fingerprint. But then, when I was a graduate student, almost all the laboratories have had the IR spectrometer, infrared spectrometer, and not limited to organic compound, organic chemistry. In organic chemistry laboratory, measure those products by taking in IR spectrum. And at that time, the range, wave number region from 650 to 1300 wave number range is called fingerprint region. And this is the IR spectrum of salicylic acid. And if you prepare the compound, showing the IR spectrum, the same as in this fingerprint region of this compound, it is possible to say your prepared synthesized product is salicylic acid. And at that time, nobody knows the correct meaning. Why those peaks appear in this region, in wave number region, and why the intensity is different depending on the wave number. Nobody knows. But this peak can be assigned to carbonyl or something, so it is possible, but not completely. So that is the same as fingerprint. Fingerprint has no meaning, and this fingerprint region has no meaning. But nowadays, so it is possible to simulate this IR spectrum only by putting this structure. It is possible to simulate this IR spectrum, and that means that we know almost completely the meaning of this. But at that time, when I was a graduate student, more than 40 years ago, at that time, nobody could say the detailed explanation of those peaks and just use as a fingerprint. So if we have the fingerprint for solid inorganic compound, it is possible to identify the inorganic solid compounds. So that means without using those conventional analytical data, using a fingerprint, Erdtcbb pattern as a fingerprint, it might be possible to identify inorganic solid compounds. The Erdtcbb pattern can be used as a fingerprint. And at that time, no need to use these conventional analytical data, as I told you, for when comparing with Steve. So what is Erdtcbb? ERDT is energy reserved distribution of electron traps, ERDT, and CBB is conduction band bottom position. So the combining those two data, ERDT and CBB, Erdtcbb pattern, can be a fingerprint, at least for identification of inorganic compounds such as metal oxide powders, but not limited to metal oxide powders. And what is the ERDT and CBB? So recently, we have developed new type of measurement of solid compounds, and that is called reversed double beam photoacoustic spectroscopy. So the meaning of reverse is we had already another technique, double beam photoacoustic spectroscopy, that reversed means the two beams, the function of two beams are changed. So therefore, we call this reverse double beam photoacoustic spectroscopy compared with ordinary the previously developed double beam photoacoustic spectroscopy. That is, we use two beams. One beam is used to excite electron in valence band of material to electron traps. What is the meaning of electron traps? The electron trap is just the ideal the electronic level, just a level. And electron trap means vacant electronic state. That means without electron in those traps. And they can accept the electrons. So that is called electron traps. Okay, then there are vacant electronic states and electron filling valence band can be excited directly to electron traps. And for example, if the positive hole produced simultaneously is used by using the electron donors, for example, alcohol, the electron, once excited electron can't go back to valence band. So the electron stay in this electron trap. And that is this compound is reduced. So for example, titanium oxide can be reduced by hydrogen, and that produces Ti3+. That is Ti4+ cation. One electron is injected to Ti4+ and becomes to give Ti3+. And probably you know that this Ti3 containing titanium oxide turns blue or blue-gray. So that means red light is absorbed by this. So that means the new absorption in the visible region appears. So then as I told you, two beams are used. One is for excitation, and the other beam is to detect the newly produced photoabsorption. So by using the PAS, photoacoustic spectroscopy. The photoacoustic spectroscopy is a very, very conventional, very, very old method. Probably you know the name of inventor of telephone, Alexander Graham Bell. He developed this technique, PAS. And the principle is very, very easy. So if the compounds is irradiated by modulated light with different intensity, modulated light, for example, 35 Hertz. And if this sample absorb this light, the photoabsorption gives higher energy state. And almost all those higher states can go back to ground state by releasing heat that is provided by photoabsorption. And the modulated light is used. Once the heat is generated, and for lower energy part, that is released, that is cooled again. So heat, cool, heat, cool, heat, cool. So that means the material is expanded by released heat and shrink. Expand, shrink, expand, shrink, with the same as the modulated light modulation. So that means the solid is vibrated to give sound. And the microphone equipped in this cell detect this sound signal. And if this sample doesn't absorb light, no signal happens. And even if this is reflected, so in the ordinary spectroscopy, if that is, how to say, diffused or reflected, without a photoabsorption, that can be detected as photoabsorption in the ordinary spectroscopy. But for PAS measurement, only absorbed light is detected. Even if this is reflected or diffused, nothing happens. When the material absorbs light, it gives a sound. So therefore, that is very, very good way to measure the solid photoabsorption. And secondary beam that is modulated, right, is to be used for detection of newly developed color due to the electron accumulation in electron traps. And the excitation light wavelength is scanned from a longer wavelength region to shorter wavelength region. So that means from lower energy side to higher energy side. And if the energy is low, only lower energy electron trap can be filled. And the wavelength is scanned to higher energy side. The higher energy electron traps are filled then. So then the electron trap in those material is filled from lower side to higher side. So this is the principle of reverse double beam photoacoustic spectroscopy. And this is a real setup. This is just an old one, but the principle is the same. This is a cell. And the inside of the cell, the sample is loaded like this. That is almost the same as for XRD. The dimple, the powder sample is filled. And also the thin film material on the substrate can be measured using the same technique. And in the cell, the microphone is equipped. And the two beams that is combined with this, the beam mixer is introduced to sample cell. And the detection of signal from microphone is the detection can be made by using the locking amplifier. And this is the actual results. And the top panel is the result of photoacoustic signal change by scanning the excitation light from longer wavelength side to shorter wavelength side. And the accumulation starts from this wavelength, about 550, and increasing gradually, and suddenly steeply increased at about 430 nanometer. And then at the 350 nanometer, that is almost saturated. So this is the total accumulation. In this lower energy region, the accumulation is not so much. And at the high energy part, that is much. And therefore, this is accumulation. So therefore, by differentiation from the lower energy side to higher energy side, it is possible to have the energy reserved distribution of electron trap in relative value. So the important point is the PAS signal, photoacoustic signal, is just a relative, no information of absolute photoabsorption. So therefore, it is necessary to convert this relative value into absolute value by using the coefficient determined by the chemical titration method for titanium oxide. So at the present, only titanium oxide and cerium oxide can be determined, can be used for determination of absolute amount of electron trap. But by using this coefficient, it is possible to determine the electron trap ET density in the unit of micromole per gram unit. And by using the same instrument with one beam, single beam measurement, that is just the ordinary PAS spectroscopy, it is possible to measure the photoabsorption spectrum-like signal. That is something like this. That is almost the same as the the absorption spectrum or reflectance spectrum of samples. And it is possible to determine the band gap from the photo absorption edge wavelengths. Here, that is about 3.0. So that means about 400 nanometer. That is about 3.0 electron volt band gap. And as I told you, the excitation to electron trap happen from valence band. And the lowest energy required for excitation is from valence band top position. So therefore, in practice, this energy is shown in difference to valence band top position. So here, 1.9 electron volt, that means from the valence band top position. And the the band gap energy is energy difference from valence band top and the conduction band bottom. So therefore, same as in this energy distribution of electron trap, the conduction band bottom position can be shown like here in the line here. That is the conduction band bottom position in difference to valence band top position. And this is the example of one of the commercial titanium oxide, STF4. And 152, this is the total density of electron trap measured in this technique. And this is determined by conventional nitrogen adsorption measurement and specific surface area of 52. And by using XRD technique, the almost annotated structure, but small amount of router is also included. But without using those conventional analytical method, it is possible to show this is STF4 only by using this Erdtcbb analysis. Then I will show you this. Okay, this is the results of Erdtcbb pattern analysis for commercial titanium oxide samples. And annotated sample, that is shown A, and annotated rich with small amount of router A plus small r, and the router rich R plus small a, and router titanium oxide and brookite. But that is just determined by XRD. And we no information about the non-crystalline part might be included in those materials. And you can see the ERDT pattern and the CBB position and the TD for those samples. Yes. And probably you can see the difference of Erdtcbb pattern depends on this crystalline structure. Probably that is almost okay. And the important point is amorphous material. They previously available. Now it is impossible to get, but previously we can purchase amorphous titanium oxide. The important point is amorphous titanium. The composition is determined to be TiO2, but no crystalline phase, no peaks in XRD. But the composition is TiO2. That can be amorphous titanium oxide. And this also shows the similar ERDT pattern, although that the position is a bit higher than the other crystalline material. But even if that is completely amorphous, no crystalline phase, the ERDT pattern, ERDT and CBB pattern can be measured by using this technique. Another important point is if the total density of electron traps are plotted against a specific surface area, I cannot say that is a good linear relation, but actually the tendency is clear. With increase in specific surface area, the total density is increasing. And some y-intercept here, not completely zero, but almost zero. And the slope tells that about 1 electron trap per square nanometer. Please remind us that surface hydroxyl group, OH groups on ordinary titanium oxide, that the surface density is about 2 or 3 hydroxyls per square nanometer. And this number, about 1 electron trap per square nanometer, is not so different from those surface hydroxyl group. And the important point is, if this is almost linearly changing depending on specific surface area, that means those electron traps are only located on the surface, or this technique only measures the surface electron trap. Even if the bulk electron traps are there, it is impossible to measure. But we cannot determine which is the truth. But anyway, the only surface electron traps are measured. And this almost constant density tells those electron traps are not something like a point defects accidentally prepared on the surface. Probably surface reconstruction structure have some certain density, specific density of electron traps. So this is our speculation. But the important point is we measure surface electron trap. That means that surface structure are measured by using this technique. Okay, going back. This is only part of the results. And A means from XRD result, only anatase is included, three samples. And for rutile, 3 samples. Only rutile structure is given by XRD. And sorry, CBB position for rutile is about 3.0. And for anatase, that is 3.2. And even if the different samples are used, if the bulk structure is the same, this position 3.0 and 3.2 is the same. So that suggests that the CBB position depends only on bulk structure, not surface structure. But for example, the TiO13 and TiO1, almost the same specific surface area, has almost the same specific surface area, but you can see the difference in ERDT pattern. And remember, ERDT pattern, that is electron trap distribution, electron traps are located on the surface. And such a difference in ERDT pattern, even for the same bulk material, bulk structure, and almost the same particle size, the surface structure might be different depending on the kind of samples. So that is the ERDT pattern, at least ERDT pattern is not reflected the bulk structure. Probably only surface structure is reflected in ERDT patterns. So probably this is the first example of macroscopic surface analysis. But we don't know the meaning of this pattern. Yeah, but still, there is some difference. Okay. And this is, again, only the part of commercial titanium oxide samples. And you can see almost all those commercial titanium samples gives a different ERDT CBB pattern. So that means that, okay. And here, the important point is this is one of the titanium oxide sample provided by Catalyst Society of Japan as a code name of TiO7. And we measured TiO7 in different bottle, and the pattern is completely different. Completely different. This is the code name the same, then probably you see only the white powder here. And another bottle contains white powder. And the other one contains white powder. And all the code name of those bottles are TiO7. But the content gives a different pattern. So that means even if probably the same CBB position tells the bulk structure is the same, but the surface structure is completely different depending on the sample, even if the same code name is here. Okay, anyway, this Erdtcbb pattern, those Erdtcbb patterns can be used as a fingerprint of metal oxide powder. This is just the example of titanium oxide, but almost all the metal oxide powders give such a pattern. And why they are different depending on the sample. So as I told you before, the minimum requisite for identification of the solid compound is to determine the bulk structure and the bulk surface size and the surface structure. The three structure, at least three structure must be determined. And as I told you, the CBB position tells the difference in bulk structure. If the bulk structure is the same, CBB position the same. And the total density E gives, that is almost proportional or the changing depending on the specific surface area. That tells the surface size or particle size. And then, as I told you, ERDT pattern reflects the surface structure. So therefore, CBB position tells the bulk structure, TD position is reflects the bulk size or surface size, and the ERDT reflect the surface structure. So therefore, three structural parameters are included in this. So therefore, the different sample gives different patterns. At least the part of them are different. This is the example of results, Erdtcbb pattern or patterns of metal oxide. Zinc oxide, strontium titanate, molybdenum oxide, enzyme oxide, bismuth oxide, tungsten oxide, and cerium oxide gives those ERDT pattern. And probably they are all unique. And please remind that even if the same composition, for example, strontium titanate, different strontium titanium gives the different ERDT pattern, even if the CBB position is the same. Probably the bulk structure is the same, the CBB position is the same. But if the surface structure is different, the different ERDT pattern can be measured. So again, this can be. But the important point is the density given by this x-axis. That is just a relative density. If that is titanium, the signal intensity tells that the absolute density, but that might be different. But if you compare the same metal oxide, for example, molybdenum oxide, the difference in the total density, relative, even if that is relative, it is possible to compare. And you can see the difference in total density, at least relatively. This is the results of anodic titanium nanotubes. And if you have the experience to read a paper on this titanium anodic nanotube, they are prepared by anodization of metallic titanium plate. And this gives the surface oxide layer. And the structure is very unique. That is nanotube structure. And probably in those papers reporting this anodic titanium nanotubes, the same picture, same images are given. And no other data, probably. Because there is almost no structure, the analytical method to determine the structure of a nanotube, just knowing the size of pore and length and density. checked by this SEM, scanning electron microscopy. And this is because it might be titanium and white prepared from titanium metal. So therefore, that might be titanium oxide, TiO2. But the X-ray XPS, X-ray photoelectron spectroscopy only tells that that is similar to that TiO2, just. And no XRD peak, that is almost amorphous. So no XRD peak. And it is impossible to get any structural information except for this same picture. And when they are prepared in different conditions shown in this, even if the same voltage, but using this different solvent and the different addition of water and different time of anodization and heating afterwards. And you can see the difference. Yes, different same images, but they doesn't give any information how they are different. Even if the performance of those titanium nanotubes are completely different, there is almost no difference, just a nanotube. But our newly developed technique tells those difference in Erdtcbb pattern. For thin film, that is 3 micrometer. 3 micrometer film is, in ordinary sense, that is not thin, that is a thick film. But the density is very, very low. So therefore, even if this is 3 or 2 micrometer thickness, the actual density, actual weight of titanium is very, very low. So it is impossible to see any ERDT pattern. But if the thickness is high enough, it is possible to see those Erdtcbb patterns. And from this SEM image, we can't say only this is small pore size, and this is small, and this is middle, this is middle, and this is large. Only those differences. But the Erdtcbb pattern clearly tell those difference. And at least 3 signals here at 3.6 and 3.3 and 3.2. And this contains all 3 components. But this contains only second and third component. And probably this high energy part is isolated amorphous. And this part is amorphous in contact with anatize, and this is anatize. And you can see those differences in this ERDT pattern. But again, those ERDT pattern doesn't give any direct information on the structure, but it is clear they are different in structure, at least for surface structure. And as I told you, for commercial titanium, the amorphous material can also be analyzed. And this is the result of niobium oxide, Nb2O5. And those gray part, 6 samples, are completely amorphous. That means no XRD peaks are given. But we can see the Erdtcbb pattern like this. And that is not so different for crystalline materials. So for ERDT pattern tells the surface structure. And even if the bulk structure is amorphous, non-crystalline, and if the part of them contains a crystalline part, but the surface structure is not so different. And the left top and the left bottom, they are different material, starting material of niobium, Nb2O5. Probably this is niobic acid. And this probably niobium oxide amorphous. And by heating at this temperature, the pattern changes. And you can see the difference, completely different Erdtcbb pattern of the left two samples, starting materials. And that means they are different. But by heating at this temperature, the pattern becomes a bit similar. So the starting materials are different, but the heating at the temperature gives the almost the same material, probably neobic acid, but still not the completely crystalline material. And all six samples are amorphous, and this is TT. That is the name of crystalline phase of niobium, and TT and the T crystalline phases are detected in XRD. But you can see for TT materials, the peak position of ERDT a bit lower compared with amorphous one. So that reflects the surface structure, depending on the bulk structure, amorphous or crystalline. So even though amorphous or amorphous containing material, it is possible to analyze by using this technique. And this is the results of titanium thin film, probably about 1 micrometer thickness. And that is completely transparent. And it is almost impossible to take XRD pattern because of the very, very low thickness, small thickness, and also they are amorphous. But depending on the preparation conditions, the patterns are different. And probably this position, about 4 electron volt, that is amorphous titanium. And the peak position is but a bit lowered with this sample, and are much more shifted to this sample. Probably this they crystallized a bit compared with those materials. So the other analytical method don't give any information of structural difference of those titanium films, but this technique tells clearly those materials are different. And of course, the photocatalytic activity must be completely different, but I have no information. This is just asked from private company, and I have to hide this number or condition of making this titanium, but they have some information on the analytical results or photocatalytic activity data, and it is possible to explain. Might be possible to explain by using that difference in those Erdtcbb patterns. For insulators, as I told you, almost all the metal oxide I have shown that is N-type semiconducting materials, and some P-type semiconducting materials, for example, nickel oxide doesn't give Erdtcbb pattern. Probably N-type semiconducting material might be measured, can be measured. But the insulators, lanthan oxide that has very wide, large band gap can be detected. And the zirconia, silica, and alumina, SiO2, Al2O3, ZrO2, they don't give ERDT pattern if they are pure. But if that is doped or with some impurities, they give those ERDT patterns. And probably this is not proportional to the specific surface area, but depends on the amount of doping or impurities. And that is very important point. And any material can be detected something. If we can detect a very small signal by using the special technique, it is possible to analyze those samples. But anyway, we have no limit of measurement. And if you have some materials to be measured, we are very happy to accept to measure. And even if that is insulator or p-type semiconductors, but it is possible, might be possible to measure. So anyway, that we can measure those patterns even for insulators. And Son-san in Kyushu University and with the collaboration of Professor Sasaki Sensei, they prepared the C3N4 graphitic carbon nitride that is categorized in semiconductor, and that might be inorganic compound. And by changing the starting material, it is possible to prepare the different types of carbon nitride that is doped materials. But the XRD pattern gives almost the same patterns. And it is a bit difficult to make different, to find the difference of those samples in XRD patterns. But by measuring the Erdtcbb pattern, that is very clear. If the ordinary starting material contains only C and N, that gives the peak around 2.8 electron volt. But if the precursor contains oxygen, then probably the surface or part of bulk is doped with oxygen. That gives the lower energy side peaks here. That is very clear. And also, if this carbon nitride prepared in nitrogen that is heated in air or prepared in air, a bit the small tailing at the lower energy side that is similar to prepared by oxygen containing precursor is the tailing appeared here. So probably this part reflects the surface doping with oxygen. And if the precursor containing sulfur, the more lower energy side peak appears. And probably this is also reflecting the surface structure containing sulfur. And probably this is the only one possible analytical method to characterize those doped carbon nitride materials. And they are very, very active, and already the 4 papers had been published using the data of Erdtcbb patterns for characterization. Okay, then to use this Erdtcbb pattern as a fingerprint, we tried to analyze quantitatively the identicalness, similarity, and difference of Erdtcbb patterns. Probably, as you know, that for the criminal detection, the fingerprint is analyzed, and there is a rule, some local rule to analyze quantitatively the similarity or differentness of fingerprint, and we should find the way to quantitatively compare the Erdtcbb patterns. And then we selected one commercial titanium oxide, annotated titanium oxide, FP6, provided by Showa Denko, and we measured Erdtcbb pattern of samples taken from the same bottle, but almost the same position in the same bottle. And we could measure the almost similar patterns. And by seeing this, you can see almost the same, but we need to analyze quantitatively. Okay, so we selected 3 parameters, the identicalness, similarity, or differentness of three points. One is Erdtcbb pattern, this one. That is the shape of Erdt curvature is compared. And the absolute value is not considered, just the shape. And this is called zeta S. That is from 0 to 1. 1 means the shape is completely the same. 0 is completely different. And total density here, provided by the triangle bracket. That is 151, 163, and 155. And the identicalness, degree of coincidence of total density is also calculated to give the value between 0 and 1. 1 is completely the same, 0 is completely different. And the CBB portion is also compared quantitatively to give the value of degree of coincidence of CBB within the range of 0 and 1. 1 is the same, and the 0 is completely different. And the standard deviation of those data, surface curvature, the Erdt pattern curvature, pattern shape, and the density, and the CBB, the standard deviation is very, very small for CBB. That if the bulk structure is the same, CBB position is the same, so the position is almost the same for those materials. And this is, how to say, almost no deviation. But the density is changing depending on the measurement time. So that has a bit higher standard deviation. So therefore, we put weight to multiplying those 3 degrees of coincidence. For small standard deviation, degree of coincidence of CBB, that we put a heavier weight too. And for large standard deviation, degree of coincidence of density, total density, we put the lighter weight. And this is just an inconvenience, not tentatively determined, but we can calculate the total degree of coincidence of this Erdtcbb pattern by multiplying those 3 partial degree of coincidence. And the 3 pairs of those 3 measured samples, we measured the zeta value to be higher than 0.88. So if the patterns, Erdtcbb pattern gives the degree of coincidence higher than about 0.9, it is possible to say they are identical because those samples are taken from the same bottle. Yes, but if the sampling was made a bit different portion even in the same bottle, the another pattern gives clearly different Erdt patterns. So the higher energy side tailing or some peak appeared. And actually, the degree of coincidence of this another sample is the standard sample was a bit lower, to be about 0.7 or 0.8. So compared with the approximately 0.9 value, that is clearly different, clearly low. So this tells 2 things. One is our RDB path measurement is very, very sensitive. Even for we can detect the difference in the same bottle. And the second point is the ordinary powder sample, solid material, contains some heterogeneity. And actually, if you vibrate the bottle, such a heterogeneity must be become higher, must become higher. So the higher density grains going down, the lower density, lighter particle going up. So the different heterogeneity must be increased by shaking. And the ordinary transportation gives some shaking. And when we receive those samples, so the powder has some heterogeneity. So this is important. So we couldn't measure those heterogeneity in the sample in the bottle because the bulk structure is almost the same. Probably such a difference suggests the difference in surface structure. Even if that's almost the same particle size and same bulk structure, if the surface is different, we can detect those differences. Okay, then, this is the part of results of degree of coincidence measurement for pairs of commercial titanium oxide samples. This is just only the part, and probably you can see, you must see the degree of coincidence is very low for almost all the pairs of the commercial titanium oxide samples. The lower than 0.5 or even almost 0. That is natural, yes, because they are provided as different titanium oxide samples. So therefore, it is natural to see such a difference. But some pairs of samples, titanium oxide sample, gives the total degree of coincidence higher than 0.6. So 6 red bars are here. And this is the top 7 pairs of titanium. And the first one is TiO4 that is provided by Catalyst Society of Japan and the WACO sample that gives the total degree of coincidence 0.788. And the important point, one point is the rank 2 TiO4 and P25, TiO8 rank 3, TiO8 and ST01, and rank 7 TiO11 and FP6. They are provided in different way, but that is the same product provided by different organization. So we know that the TiO4 is P25, the source material is the same. And therefore, it is natural to see the high degree of coincidence of those rank 2, rank 3, and rank 7. But that is actually smaller, lower than 0.9 that is provided by the sample taken from almost the same portion in the same bottle. And for this pair, TiO11 and FP6, even though they are same product, that is almost very low. Not so very low, but relatively low degree of coincidence. And that tells, even if the same code name prepared in the same batch or same process, even if the same product is obtained in the same procedure, but the storage condition might give some difference. That is a very important point. And the very interesting point is WACO. WACO appears twice in rank 1 and rank 4. And remember that TiO4 and P25 is the same as in rank 2. So probably WACO, a private company in Japan, they purchase P25 and sell as their own product. Probably. I call WACO company. So probably your product might be P25, but they say that is a secret and they cannot give answer for that. Anyway, important point is this column. This is zeta PC. Zeta PC is a degree of coincidence of photocatalytic activity That is average value for 3 photocatalytic reactions, completely different photocatalytic reaction conditions. And rank 1, TiO4 and WACO gives the degree of coincidence of photocatalytic activity of higher than 0.9. That is average of 3 reactions, 0.9. So that means TiO4 and WACO gives almost the same photocatalytic activity. And with the decrease in degree of coincidence from 0.788 to 0.615, the degree of coincidence photocatalytic activity is decreasing. So it is possible to see the relation between this zeta value and zeta PC value. So similar sample gives similar photocatalytic activity. Yes. So therefore, even if we don't know the source of WACO sample, that can be regarded as P25. So because they show the different photocatalytic, they show the almost the same photocatalytic activity. So we need to see the level, even if that is given, shown as TiO4, P25, or WACO, that they are almost the same, and they must show same photocatalytic activity. And that is not limited to photocatalytic activity. Another analytical results or property or performance or activity must be the same. To make it clear, the degree of coincidence of photocatalytic activity is plotted against the degree of coincidence for pairs of titanium oxide samples. And red circle gives the degree of coincidence of photocatalytic activity for methanol dehydrogenation, producing hydrogen from methanol aqueous solution of methanol. And that is 1 degree of coincidence of photocatalytic activity. 1 means the activity is the same. That is not absolute value, just comparing the 2 titanium oxide photocatalysts for hydrogen evolution. The green one is carbon dioxide production by decomposition of acetic acid. And black circles, closer circle, that is for degree of coincidence photocatalytic activity of oxygen evolution reaction. And almost no relation, just scattered. But here is a line. So high degree of coincidence pairs higher than 0.6 pairs don't give lower degree of coincidence of photocatalytic activity. That is, every time high degree of coincidence of photocatalytic activity. Yes. To make it clear, or this tendency, the 7-point non-weighted moving average, that is the one of the averaging method for such a scattered results. And again, here, if the degree of coincidence is lower than 0.6, that is scattered so much. And this is averaging. So therefore, this position, for example, this black plot for oxygen evolution, that is very low. And 1 pair of titanium oxide with degree of coincidence about 0.6 gives a very low value. And this proves the other data to lower side. And for this red one, the 0.1 degree of coincidence about 0.1, a sample pull up the other samples. So anyway, that is so much scattered. But if the degree of coincidence is higher than 0.6, the degree of coincidence of catalytic activity is increasing. And at the 0.8 or 0.85, the degree of coincidence of photocatalytic activity becomes almost 1. That means same photocatalytic activity. So we submitted the paper including this data. And the one reviewer claims that, of course, If the sample is similar, they must show similar photogalactic activity, and no need to report such a data. That is natural. No need to say no. The result tells that we can determine quantitatively the similarity or identicalness of solid compound for the first time. No other technique doesn't give such a quantitative value for comparison of solid materials. So this can be published. Yes, this could be published. And among the authors of this paper, only I believe that this can be called elephant plot. Elephant is a holy animal in some Asian countries, and that is a very holy plot. And I love this plot as an elephant plot. And this is the first time to give such a pattern, shrinking, and increasing. So this is the first example of elephant plot, and this is a new concept to compare the similarity of solid materials. Then we tried to publish. First, starting from Nature, Science, something. So all rejected. And at last, probably at the 7th time or 8th time, that is accepted by Chemical Communication. That is published in 2016, 6 years ago. Not so recent, but 6 years ago, this is published in Chemical Communications. And that is open access. So you can download freely from the website of Royal Society of Chemistry. Yes. And then for Erdtcbb pattern analysis, it is very important to have some, how to say, trend. So that is, as I told you, if the same Erdtcbb patterns are obtained for pairs of samples, they must show same property activities. The example is photocatalytic activity. But, for example, a kind of metal oxide can be used as a polisher, polishing agent. And the polishing ability is just a physical, no chemical. Probably no interaction or no participation of electron trap for polishing ability. But if the same patterns of polishing material is obtained, the polishing ability is almost the same, even for those physical properties. So because the ERDT pattern is just a fingerprint, and if they are same, they must have same material. So they must show same property, activity, and performance. But if the same property or activities are obtained, the Erdtcbb pattern cannot be the same. The different pattern sample gives the same activity of or performance accidentally. And only this way, same pattern, same activity, same property. And then different property or activities are obtained. They must show different Erdtcbb pattern, because if they are similar, that must be similar. So different performance, different activity, different property must give different Erdtcbb pattern. But if the Erdtcbb pattern are different, completely different, sometimes the performance is the same accidentally. So therefore, only this way, from this side to this side. For top one, this side to this side. So this is important. So therefore, if only by seeing the patterns of samples, it is impossible to predict the similarity or difference. of performance. So we check this. For those three photocatalytic photocatalytic reaction producing hydrogen, carbon dioxide, and oxygen. So completely different conditions and completely different activity. And some titanium oxide give higher activity in hydrogen evolution, but not so much in carbon dioxide production, or something like this. And we compare the Erdtcbb pattern in order of photocatalytic activity of those three reactions. And please note that for hydrogen evolution reaction, the in situ platinum deposition is required. Without this deposition, no hydrogen evolution is obtained. So therefore, we put a small amount of precursor of platinum, and photoirradiation gives the deposition of platinum on the surface of titanium oxide. So this might be two-step reaction. So anyway, for those three photocatalytic reactions, the patterns, Erdtcbb patterns are arranged in order of photocatalytic activity. The left top is the highest with relative activity 100. And this is decreasing, 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 decreasing. And the left bottom is the worst. And for hydrogen evolution, the worst one is relative activity is 6. For carbon dioxide, that is 10, and oxygen, that is 1. And almost no relation, not so good patterns. But if you see the patterns of relative activity higher than about 70%, the yellow one, for carbon dioxide and oxygen evolution case, that is similar, not so different. But below 70% relative activity, the pattern, the neighboring pattern doesn't give not so same. Completely different pattern appears in middle or low activity samples. And for hydrogen evolution case, that the pattern, there is no similarity can be obtained. For those two reactions, what does it mean? Probably the activity depends on different kinds of properties. For example, the surface area, specific surface area or particle size give the very, very strong effect on photocatalytic activity. And the other one gives the different, for example, shape, particle shape or particle thickness or secondary particle size may give decisive factor, decisive influence on photocatalytic activity. And for those low activity samples, the reason for lowering the total photocatalytic activity is different depending on samples. So therefore, neighboring patterns don't give the similarity. But for higher activity samples, that is all the properties, structural properties are well balanced. So therefore, that is optimized. They're probably similar, even if the different company, private company produces those samples, they're probably similar preparation method, procedure gives a similar well-balanced samples. So that means for carbon dioxide and oxygen evolution case, it is not easily expected that much more higher activity sample can be prepared by using ordinary synthetic method. Probably this is the maximum, highest activity. But for hydrogen evolution case, that is randomly, the pattern appears randomly. So that means this is, as I told you, two-step reaction. Part of titanium oxide is very good for photo-induced deposition of platinum. And once that is platinized, again, the difference in hydrogen evolution reaction depending on the structure of titanium oxide. So the different property is given by different samples. So therefore, there is almost no similarity for higher activity samples. And in the other words, that it might be possible to have much more higher activity sample by controlling the deposition, platinum deposition conditions. So therefore, that the hydrogen evolution case, that is a bit different from the other carbon dioxide or oxygen evolution case. So anyway, what we must think is the well-balanced structure is necessary. And different or lower activity sample can be easily prepared in different way. So for example, if, this low activity sample, even if we could clarify why this sample is not so high. For example, that is specific surface area is very small or some defective sites here. But if that is improved, there is no guarantee to have high energy, high activity, because the other parameter may give lower photogalactic activity. So therefore, it is necessary to be well balanced like these higher activity samples. So when I talked this story in Kyoto University, the one graduate student came to me after the lecture, and he said, do you know the Levi-His law of minimum? And unfortunately, I didn't know. So Levi-His law of minimum is Levi-His is probably you know the name of Levi-His condenser. That's the same person, Levi. And he is also working in the field of biology. And he found the rate of growth of plants depends on several parameters. And even if, for example, sunlight radiation, water, and potassium, or something. So many parameters are there. And the total rate of growth depends only on minimum. Even if the other parameter is very, very good, the total growth rate is determined by this minimum. So this is well known as Levi-His or Dobenic's barrel. So the water flows out from this minimum. Even if the other part is very, very high, the water level is determined this minimum. So that means for photocatalytic activities, the lower photocatalytic activity can be made by different way. So therefore, it is necessary to make well-balanced barrel to keep high water level. And probably you know that Tolstoy, the very, very famous novel, Anna Karenina, the first sentence of this novel is, happy families are all alike. Every unhappy family is unhappy in its own way. Yes. So happy families are very similar, but the unhappy family is unhappy in different way, not the same reason. And I want to say, active photocatalytic powders are all alike. as I show in carbon dioxide and oxygen evolution case. Every inactive powder is inactive in its own way. Yes. So we need to change our way of thinking to have high photocatalytic activity samples. So what we should think is total balance, not to make lower minimum factor, giving the decisive lower photocatalytic activity. That is very important point. And that is completely different way of thinking or design of functional materials. And I don't think that it is not only for photocatalyst, the ordinary catalyst, thermal catalyst, or the other functional materials may be controlled in such a way. So, and another important point is Erdtcb pattern reflects the total structure. So we don't know the detailed structure, what is different, but the if the Erdtcb pattern is different, the structure is different. So we might discuss the photocatalytic activity or the other performance or functional materials only by using the non-analytical results. For example, XRD, specific surface area, but no other parameters or not analyzed or not noticed difference in parameters or structures are considered. So that is important. So anyway, those stories are given in a recent review paper published in Catalyst Science and Technology. The title is Happy Photocatalysts and Unhappy Photocatalysts. So probably this is the first paper having the title Happy and Unhappy. And this is, of course, downloadable freely. This is open access, and you can download this freely from the website of Royal Society of Chemistry. Yes. So then, one short story. So we have succeeded in specifying the sample. And as you see, we can specify the mixed material. For example, anatase and rutile are mixed. Those samples can be also measured. That is, we have some fingerprint of those mixtures. And please remember that for organic compounds, identification is made for pure materials, not mixed one. For mixed material, it is impossible to identify using fingerprint or the other technique. But for solid material, even for mixed material, that can be. So then, what should consider is what is the pure material, pure solid material. So they are mixed material, and it is necessary to analyze how they are mixed. So to make it, it is necessary to have pure compound. Without pure authentic sample, it is impossible to analyze mixed compound. Of course, we can take fingerprint for those mixtures, but to characterize why those ERDT patterns appears, depending on the surface structure, it is necessary to have pure samples. Yes, and this is completely different. So probably what we say pure in organic material is just purity of composition. But composition is just a composition, not a structural parameters. So we should determine the concept of purity of solid material. And one possible candidate for pure solid material is octahedral anatase particle. Yes, anatase appears naturally like this. The color is due to the doping, probably iron or the other kind of metals. But this is pure anatase crystalline. And this shape is called octahedral. And the important point is this reflects the 8 facets of crystalline. The same structure, 101. Different name, but the structure is the same as this 101 face. So all the surface has the same surface structure. And this is natural one, but we can prepare this octahedral particle. First, the Yasumoto-kun and Amano sensei prepared this from the titanium nano wires. And that is very small particle, about 20 or 50 nanometer size, but very high content of octahedral particle exposing only one type of facet, 101. Okay, so if the crystalline structure, crystalline phase is all anatase, 100% anatase, that can be pure in bulk structure. And if all the particles are of this octahedral shape, they exposing only 101 facet. Therefore, the surface structure can be pure. And if the particle size is the same, the very small distribution, it is possible to say size is pure. So if we can prepare the same sized octahedral particles, that can be pure onsetting sample. 3 structural parameters, bulk structure, surface structure, and size. All these are pure. So it is possible to say that is pure material. Okay, you mean attending this last lecture? He made the very good effort to make high purity octahedral particles. And by changing the preparation conditions and he got very high purity anatase particle. The highest one is 99%. Honestly speaking, it is actually no method to determine the true purity of crystallinity because we don't have 100% purity difference sample. So therefore, the calculation tells that the purity is higher than 100%. So probably the authentic sample we used as a standard 100% crystalline cannot be totally 100%. And so anyway, very, very high crystalline purity. And also the purity of shape that is higher than 90.92. And for small particle, the content is not so high, but still almost 80%. And the size that is in nanometer, that is determined by measuring the size from bottom to top, and the average is calculated like this. And it is possible to calculate the density or weight of one octahedral particle. And also we can calculate the surface area of one particle of size shown here. And actually, the measured specific surface area is almost the same as this calculated value calculated from this size. So that means the purity is very high. Then that is like this. And okay, and then the particle size distribution is not so good, but actually we can say that the particle size within 20%, the distribution is about 80%. More than 80% particles are in the range of plus minus 20% in size. Not so good, but not so bad. The almost the same particle size can be obtained. And then by measuring the Erdtcbb pattern, this is the result. And depending on the size, the total density is different, but the shape shown in this is the single Gaussian fit gives almost the same shape of ERDT pattern for octahedral anatase particles. And by normalization at the peak position, these blue lines for OAP sample, octahedral anatase samples, that is almost the same. And the half height width is much more narrower compared with commercial titanium oxide patterns. And that means probably the different type of surface facet gives different ERDT peak position. And they are the mixture for commercial samples. Different surfaces are exposed. But for OAP, only 101 facets are exposed. So therefore, very narrow one. And important point is the particle size dependence. Sorry, before that, this is the total electron trap density plotted against the specific surface area. And very good linear relation. For the commercial titanium oxide sample, it was impossible to say that a very good linear relation. But for octahedral particle, that is very, very good linear relation. And density, surface density of electron trap for this octahedral particle is about 0.5. That is almost half for a commercial titanium oxide sample. And the 101 facet may have lower density of electron trap on the surface. And then we obtain almost 100% anatase bulk crystal and almost 100% surface 101. But the particle size can be changed. That is variable. Even if that is pure, one size and the other, another size and the other size. So there is freedom for size. So by changing only the size, without changing bulk structure and surface structure, we can see the difference in property by changing depending on the size. And this is actual result for 3 kinds of photocatalytic reaction. And surprisingly, for oxygen evolution reaction case, the activity is increasing almost linearly with particle size. That means lower specific surface area sample gives higher photocatalytic activity. And for hydrogen evolution case and carbon dioxide production case, almost constant. No particle size dependence. So this is completely different from the ordinary observation of photocatalytic activity depending on the size. Probably for the previous papers, the data, of course, the particle size is different, but the other parameter must be changed accompanying the change in particle size. But in this case, bulk structure and surface structure is the same. Only the size is different. This is true particle size dependence of photocatalytic activity of samples. So probably this is the first results of pure true particle size dependent activity. And that can be supported by Erdtcbb pattern for purity of surface structure. Okay, so then we are very happy to accept your sample to measure Erdtcbb patterns. So many colleagues asked us to provide the Erdtcbb patterns. And this is only the example of collaborators asking us to measure the Erdtcbb pattern, not only academic in Japan and in the other states. The private companies asked us to measure, not limited to photocatalysts or titanium oxide, the other many kinds of samples can be measured. And we are very happy. And after retirement, I will continue the measurement in non-profitable organization. Again, for private companies, we asked to pay something, but for academics, please do not hesitate to send us sample to measure. No need to pay anything, only the cost for measuring. Okay, thank you very much for listening. And this is the very last lecture. And again, this unique email address can be used after my retirement. So please make contact with me using this email address. Thank you very much for listening. Thank you. And okay, but in the ordinary, the last lecture for retirement, almost no discussion time. And if you have a question or comments, please provide me by using this email address. Thank you very much. And you can use the, sorry, I will stop sharing. You can use again, the breakout room, and probably you can stay as much as you want. And I will go back home soon, but I will, if you want to have some conversation with me, please ask me, and we will move to one of the breakout rooms, and I'm happy to accept such invitation. Thank you very much. Okay, I will give some myself. Oh, Elena.
Ciao, bye.
Oh, thank you
Nice to
very much
see
for
you.
coming.
I listened to all your lecture, and I'm very happy
Thank
to
you.
see you in such a good mood and still active. We are going to remain in touch.
Okay, thank you.
For
Thank you
sure.
very much. Okay.
Okay.
小丸先生、ありがとうございます。わざわざお越しいただきまして、ありがとうございます。
どうも、ありがとうございます。
ありがとうございます。
また質問させてください。
いつでもどうぞ。サンプルも送っていただいて結構です。
そうですね。はい。
はい。まずメールでコンタクトお願いします。
はい。
はい。So, Aishen, if you have a sample to be measured by Erdtcbb analysis, please send me. So
Thank you.
We are happy. We are happy too.
Okay. Thanks. Yeah, really enjoy your lecture.
Thank you.
Ciao.
Okay.
Yes. Hello.
Hi. Thank
I'm
you
a
very
bit
much
sick.
for message poster. Thank you.
Yes, I was listening. I'm a bit sick, but I listened carefully.
Wow.
And probably with pleasure, I will send maybe some samples in the future, but
Yes.
let's...
Okay, so before sending me, so I will move to another place. So please make contact with me. That is the email
Yeah,
address.
okay, by email,
Yeah.
no problem.
Hi.
Yeah, okay. Thank you for the lecture. It was very interesting.
And are you okay?
A bit sick today. Yeah, I'm just...
Not
I
corona.
don't
Not corona.
No. Normal illness, I
Okay.
hope.
Oh.
Yeah. So...
And after for last 2 weeks, I need to arrange all the things. So everything should be discarded or given to the other colleagues. And you used the micro gas chromatograph, and that is given to the colleague.
Okay.
And
No
still remaining that the glassware for irradiation. Do you need?
Yes, I mean, if you can share with me, I will be happy.
Okay,
of course.
so if so, I will ship you or send you by how to say not a mail, postal mail, that is courier. Yes.
Okay.
Probably.
Okay.
Hi.
Okay. So thank you, and I hope we'll keep in touch.
Okay, please. Hi.
Bye bye.
Bye bye. Shinton.
Hi. It's really very great
Thank you very
lecture. Thank you
much.
so much.
Hi. So still you can ask me to measure samples.
Yeah,
probably the new organization will start in the middle of April, and we can start measuring the samples in the private space. Yes.
Yeah, thank you.
Hi.
Great.
Please do not hesitate to ask me. Thank you.
Thank you.
Bye bye.
Bye bye.